Section: Introduction. In this section, we discuss how as large language models, LLMs, become more popular, it's crucial to serve these models efficiently. However, speeding up the process of generating new text with LLMs is difficult because creating just one piece of new text requires using all of the model's parameters. This creates a bottleneck, making the hardware less effective during text generation. This issue is even more pronounced when generating text in small batches or when offloading computations, as generating a single piece of text can take as long as processing a prompt with hundreds or thousands of pieces of text on modern graphics processing units, GPUs. To tackle this problem, recent innovations have introduced the concept of speculative decoding in LLM inference, which maintains the original output distribution of the LLM. These methods use one or more preliminary models to guess the LLM's output, organizing these guesses in a structure called a token tree. Each node in this tree represents a different sequence of guessed tokens. The accuracy of these guesses is then checked in parallel through a single pass of the LLM. By using a tree structure instead of a linear sequence, we can increase the number of tokens the LLM accepts by providing multiple options for each token position. Despite the significant research on tree-based speculative decoding methods, our experiments reveal some key limitations. Firstly, we found that the algorithms used to build these token trees work well for smaller trees but are less effective for larger ones. For instance, a method called SpecInfer builds a token tree using independent sequences, but this approach has a limit on the expected number of tokens it can accept, regardless of the tree's size. Secondly, we noticed that the algorithms for choosing and checking tokens in the tree don't always work well across different settings, such as when the model is set to generate less predictable text, a setting known as low temperature, because they might keep choosing an incorrect token that seems likely according to the preliminary model. Lastly, we observed that current systems can't effectively adjust the size and shape of their token trees to work best with any given hardware setup. This is because the models that predict how much faster speculative decoding can make the process assume that the time it takes to check the tokens is constant, which isn't the case for larger trees, making these predictions unreliable for choosing the best tree dimensions. In this paper, we aim to design an optimal tree-based speculative decoding method that maximizes speed improvements on modern hardware. Achieving this goal involves overcoming several technical hurdles. We need to be able to efficiently explore the vast number of possible tree structures to find the one that will produce the most tokens. We also need to create a method for choosing and checking tokens that works well across different settings and avoids choosing the wrong token repeatedly, while still producing the correct output. Additionally, for any type of hardware, we need to figure out the best size and shape for the token tree to get the biggest speed improvement. We introduce SEQUOIA, a scalable, robust, and hardware-aware speculative decoding algorithm. SEQUOIA can achieve up to 10 times the speed of traditional decoding methods and introduces several key techniques to overcome the challenges mentioned. To tackle the first challenge, we treat tree construction as a problem of finding the best solution within certain limits and use a method called dynamic programming to find the optimal token tree structure. We show, both theoretically and through experiments, that the number of tokens generated with this structure can increase without bound, growing roughly in proportion to the logarithm of the tree's size. To address the second challenge, we improve upon the SpecInfer algorithm by choosing tokens in a way that doesn't allow the same mistake to be made twice, while still keeping the final model's output distribution accurate. We prove that this new method of choosing and checking tokens works well at both high and low temperatures and confirm this through experiments. For the final challenge, we propose a way to adjust the token tree's size and shape based on the hardware being used, by considering the time it takes to check the tokens as a function that depends on the hardware and the number of tokens. This approach allows us to find the best tree dimensions for speed improvements compared to methods that don't consider hardware differences. We conducted thorough experiments and studies to show how effective SEQUOIA is. We implemented SEQUOIA using Hugging Face and Accelerate with CUDA graphs. Our results show that SEQUOIA can speed up the process by up to 4.04 times for a model called Llama 2-7B on a single A100 GPU and by up to 10.33 times in an offloading setting on an L40 GPU. We also conducted studies that show SEQUOIA's tree structure can produce up to 33% more tokens per decoding step compared to independent sequences for trees of size 512 or less, demonstrating better scalability. Additionally, SEQUOIA's method for choosing and checking tokens is robust across different settings, providing significant speed improvements over SpecInfer and other methods. Lastly, SEQUOIA's hardware-aware tree optimizer can automatically select the best tree size and depth for different types of hardware. Section Summary. In this section, we introduce the concept of speculative decoding to enhance large language model (LLM) inference efficiency by predicting LLM outputs using token trees. We address limitations in existing methods by proposing SEQUOIA, a scalable and hardware-aware speculative decoding algorithm that optimizes tree construction, sampling, and verification processes. Through experiments, we demonstrate that SEQUOIA can achieve significant speedups on modern GPUs, outperforming traditional decoding methods and offering better scalability, robustness, and hardware adaptability. Section: Background. In this section, we delve into the exploration of tree-based speculative decoding methods. We start by discussing how these methods decide on the structure of the speculation tree, the techniques they employ for sampling and verifying the token trees, and how they can automatically determine the most suitable shape for the token tree. When it comes to constructing the tree, the most common structure used by these methods involves creating k-independent sequences, each of a certain length L, branching out from the tree's root. This root represents the current prefix of tokens. The SpecTR study also experimented with various branching patterns but found that independent sequences worked just as well, if not better, in their tests. Another approach, used by Medusa, involves building a full k-array tree. This method increases the success rate at each layer but struggles to create deep trees when the number of tokens available is limited. Moving on to how these methods sample and verify token trees, SpecInfer, SpecTR, and naive sampling all use a method of sampling with replacement from the draft model. In contrast, top K sampling picks the K tokens with the highest probability from the draft model. For verification, SpecInfer and SpecTR compare the probabilities of the draft and target models for the sampled tokens to decide which ones to accept. Naive and top K sampling, on the other hand, accept a token if it matches one from the speculated tree, based on the target model's distribution. All these methods verify the speculated token tree starting from the root and moving down, differing only in the verification algorithm used at each node. Specifically, the SpecInfer method iteratively verifies tokens sampled from one or more draft models. It compares the probabilities from the draft model to those from the target model to decide on acceptance. Although SpecInfer can sample from multiple draft models, we focus on the more common scenario where only one draft model is available, thus sampling from a single draft model multiple times. The SpecTR algorithm operates similarly, iterating through a node's children and deciding on acceptance through a sampling procedure that keeps the output distribution unchanged. A key feature of this algorithm is that it achieves a performance close to the best possible verification algorithm. For naive sampling and top K sampling, the verification process involves sampling from the target model's distribution at a node and accepting this sample if it matches one of the node's children. This method ensures the target model's output distribution is maintained, regardless of the token tree's generation method. This insight led us to prefer the top K sampling method for our experiments, aiming to understand the verification algorithm's limitations better. Lastly, the concept of a tree optimizer was introduced in the original speculative decoding paper. It involves choosing the number of tokens to speculate by maximizing a specific expression for speedup. This expression takes into account the expected number of generated tokens in one iteration of speculative decoding, the time it takes to perform one forward pass of the draft model relative to the target model, and the constant time to verify the token tree. This approach can be adapted to tree-based settings by considering the expected number of generated tokens for the best tree of a given size and depth. It's crucial to note that the verification time is considered a constant in prior work, simplifying the computation model. Section Summary. In this section, we review tree-based speculative decoding methods, focusing on how these methods construct speculation trees, sample and verify token trees, and automatically select token tree shapes. Existing methods primarily use a tree structure with independent sequences branching from the root, while some consider different branching patterns but find no significant performance improvement. Various sampling and verification algorithms are discussed, such as SpecInfer and SpecTR, which compare draft and target model probabilities to decide on token acceptance, while naive and top-K sampling methods verify tokens by sampling from the target model distribution. Section SEQUOIA. In this section, we introduce SEQUOIA, a new approach that is designed to be scalable, robust, and aware of the hardware it runs on. This approach is centered around a speculative decoding algorithm. We start by explaining how we build the structure of SEQUOIA using a method that scales well as the tree grows. This method relies on dynamic programming to figure out the best way to build the tree. We've found, both through theory and practical tests, that the number of tokens SEQUOIA can process grows almost logarithmically with the size of the tree. This is a significant improvement over other methods, which hit a limit on how many tokens they can handle. Next, we discuss how we've made SEQUOIA robust. We did this by tweaking the SpecInfer algorithm to pick samples in a way that doesn't repeat choices from the draft model. Our findings show that SEQUOIA holds up well under various conditions, unlike other methods that struggle. We also talk about how we've made SEQUOIA aware of the hardware it's running on. By adjusting the size and depth of the tree based on the hardware, we can speed things up. Our tests and theoretical work show that choosing these settings based on the hardware can lead to faster performance compared to using a one-size-fits-all tree size. Moving on to the specifics of building the SEQUOIA tree, we aim to create a tree that can generate a large number of tokens efficiently. We approach this by framing it as an optimization problem where we want to maximize the expected number of tokens produced by a tree of a certain size. We use dynamic programming to solve this problem effectively. We introduce a couple of key concepts to help with this. First, we assume that the likelihood of a token being accepted by the verification algorithm depends solely on its position in the tree. Second, we define an acceptance vector that captures the probabilities of a token being accepted based on its position. With these concepts, we can calculate the expected number of tokens produced by a tree. Our method involves finding the tree of a given size that maximizes the expected number of tokens. We do this by breaking down the problem into smaller parts and solving each part using dynamic programming. This approach not only helps us find the optimal tree size but also allows us to consider trees with a maximum depth, which is crucial for managing the speculation time based on the tree's depth. In summary, SEQUOIA represents a significant step forward in speculative decoding algorithms. It's scalable, robust, and can be optimized for different hardware setups, making it a versatile tool for processing tokens efficiently. Section Summary. SEQUOIA. In this section, we introduce SEQUOIA, an innovative speculative decoding algorithm that is scalable, robust, and hardware-aware. Our approach includes a scalable tree construction algorithm using dynamic programming to optimize tree structures, demonstrating that SEQUOIA generates tokens logarithmically with tree size, outperforming existing methods. Additionally, our robust tree verification algorithm enhances performance across various temperature values, and by optimizing tree size and depth based on hardware, SEQUOIA achieves faster speeds compared to fixed tree sizes. Section: Theoretical Results. In this section, we delve into the theoretical underpinnings of the SEQUOIA tree construction algorithm and demonstrate its scalability with respect to the size of the speculated tree. We specifically illustrate that, given certain conditions regarding the acceptance rates of the verification algorithm, the quantity of tokens produced is essentially lower than a function that increases logarithmically as the tree size expands. This finding contrasts with existing tree construction methods, which, as we have shown in a table, have a maximum expected number of tokens they can generate. To start, we clarify what it means for a verification algorithm to exhibit a power law acceptance rate with a parameter b. We then share our theorem on the scalability of SEQUOIA trees, assuming the verification algorithm adheres to this power law acceptance rate. We describe a tree verification algorithm as having a b power law acceptance rate if the probability of the algorithm rejecting all speculated children of a node is capped by a function that decreases as the number of children increases, specifically at a rate inversely proportional to the number of children raised to the power of b. This concept is inspired by our observations that the SEQUOIA sampling and verification algorithm naturally follows power law acceptance rates in practical scenarios. Moving forward, we present a theorem stating that if a tree verification algorithm operates under a b power law acceptance rate, then the expected number of tokens generated while verifying a SEQUOIA tree of size n is proportional to b times the logarithm of n divided by the logarithm of n. This mathematical relationship underscores the efficiency and scalability of the SEQUOIA algorithm. In our empirical validation, we compare the average number of tokens generated by SEQUOIA trees against other tree structures as a function of tree size, using data from Wikitext 103. Our findings reveal that the number of tokens for SEQUOIA trees increases roughly logarithmically with tree size, unlike other structures which reach a plateau. We also discuss our token tree sampling and verification algorithm, highlighting its uniqueness in satisfying two critical robustness properties while preserving the output distribution of the target model. The SEQUOIA algorithm introduces two key modifications to improve upon the spec-infer algorithm. It samples without replacement from the draft model distribution, and, if necessary, switches to a uniform distribution over all unsampled tokens. These adjustments significantly enhance the algorithm's robustness and ensure the output distribution matches that of the target model. Lastly, we prove that the SEQUOIA verification algorithm is robust, fulfilling both the optimal transport and cover properties, unlike existing algorithms which only meet one of these criteria. The optimal transport property ensures strong performance when the probability distributions of the draft and target models are nearly uniform, while the cover property guarantees efficiency when the top target model token is among the top speculated tokens of the draft model. This robustness, supported by our theorem, sets the SEQUOIA algorithm apart in terms of performance and reliability. Section Summary. In this section, we prove that the SEQUOIA tree construction algorithm scales effectively with the size of the speculated tree, demonstrating that the number of generated tokens is lower bounded by a logarithmic function in the tree's size. We introduce the concept of a verification algorithm having a power law acceptance rate and show that the SEQUOIA algorithm satisfies this property, leading to unbounded token generation scaling logarithmically with tree size. Additionally, we establish that the SEQUOIA verification algorithm is robust, meeting both the optimal transport and cover properties, unlike existing verification algorithms. Section: Empirical Validation. In this section, we delve into the empirical validation of our work. We begin by examining the average rejection rates, which are essentially the inverse of acceptance rates, for various verification algorithms. These rates are plotted as a function of the number of speculated child tokens given a fixed token prefix, across different temperature settings, 0.2, 0.6, 1.0, using the Wikitext 103 dataset for measurement. Our observations reveal that, regardless of the temperature setting, the rejection rates for our SEQUOIA algorithm decrease more rapidly compared to other algorithms. Specifically, we notice that the rejection rates for SEQUOIA tend to follow a power law pattern, meaning the rejection rate decreases in proportion to the inverse of the speculated child tokens raised to some positive power. Additionally, we find that while the SPEC-TR and SPEC-INFER algorithms perform relatively well at higher temperatures, they face challenges at lower temperatures. Conversely, the top-K sampling method shows better performance at lower temperatures. Moving on to the hardware-aware tree optimizer, we introduce our method for selecting the optimal tree size and depth for SEQUOIA in a way that considers the specific hardware being used, aiming to maximize the speedup achieved by SEQUOIA. We explain that, unlike previous approaches that could optimize the speculation budget without considering hardware specifics, SEQUOIA requires a hardware-aware approach. This is because, for larger trees, the time taken for verification cannot be assumed to be constant and independent of the tree size. Through empirical testing, we demonstrate that choosing the tree size and depth with hardware considerations in mind can lead to speedups of up to 40% compared to baseline methods. In terms of the algorithm for selecting the optimal tree size and depth, we describe a process that involves calculating the expected number of tokens generated by verifying a SEQUOIA tree of a certain size and depth. This calculation is done using dynamic programming. We also consider the time it takes the target model to verify a certain number of tokens, which is hardware dependent, and compare it to the time taken to verify a single token. Additionally, we factor in the time to draft one token relative to the time to verify one token. Our goal is to optimize these parameters to achieve the greatest speedup with SEQUOIA. We suggest conducting a grid search over possible tree sizes and depths, using empirical measurements of these time factors on the specific hardware used for inference. It's important to note that for batch sizes greater than 1, the formula for calculating speedup is adjusted to account for the verification of a tree of size n for each batch element. In our theoretical analysis, we explore the properties of the SEQUOIA speedup equation to understand why selecting the optimal tree size and depth is crucial and why it must be done in a hardware-aware manner. We observe that the numerator of the speedup equation increases roughly logarithmically with the tree size, while the denominator increases linearly. This indicates that there is an optimal tree size that maximizes speedup. We also note that previous methods could simplify their calculations by assuming a constant time factor, but this assumption does not hold for SEQUOIA due to its more sophisticated modeling. Finally, we present empirical validation showing the speedups achieved on various types of hardware when selecting the tree size and depth based on the correct time function, as opposed to choosing a fixed tree size. Our findings indicate that using a hardware-aware approach to select these parameters can result in significant speedups, up to 40%, compared to using fixed values across different hardware setups. In our evaluation, we aim to show that SEQUOIA can significantly accelerate large language model (LLM) inference in terms of wall clock time. We present our end-to-end system results, demonstrating substantial total speedup. We validate our claims that SEQUOIA is scalable, robust, and hardware-aware by showcasing its superior end-to-end performance, its ability to generate more tokens on average compared to a tree of independent sequences, its robustness to temperature and top P settings, and its effective hardware-aware tree size and depth optimization. Section Summary. In this section, we conduct empirical validation by plotting rejection rates for different verification algorithms against the number of speculated child tokens at various temperatures on Wikitext 103. We observe that SEQUOIA exhibits faster rejection rate decay compared to other algorithms, following a power law decay pattern. Additionally, we demonstrate that selecting the SEQUOIA tree size and depth in a hardware-aware manner can lead to up to 40% speedups relative to baselines across different hardware types. Section: End-to-End Results. In this section, we share our findings on how SEQUOIA enhances the speed of decoding large language models, LLMs, in different computing environments. Specifically, we found that SEQUOIA can accelerate LLM decoding by up to 4.04 times on an A100 GPU when the entire process is conducted on the chip. When we offload some of the work to an L40 GPU, the speedup can reach up to 10.33 times. Our experiments were conducted using two sets of models, the Llama and Vicuña models. For tasks performed entirely on the chip, we used the Jack Fram, Llama 68 meters, JF68M, and Princeton NLP, Sheared Llama 1.3B, SL 1.3B, as our initial draft models. Our target models in this scenario were Llama 2-7B, Llama 2-13B, and Vicuña 33B. For tasks where we offloaded some of the work, our draft model was Llama 2-7B, and our target model was Llama 2-70B. We evaluated our approach using the C4N validation dataset, Open Web Text, and CNN Daily Mail, sampling 200 examples for each experiment. Both the prompt length and the generation length were set to 128 tokens. We tested SEQUOIA on different hardware setups, including on-chip experiments on L40 and A100 GPUs, as well as offloading experiments on an L40 GPU. We also compared SEQUOIA's performance against SpecInfer using different tree structures to understand its efficiency better. In terms of implementation, we utilized transformers for the on-chip setting and the Accelerate CPU offload API for the offloading setting. By determining the optimal tree structure in advance, we were able to leverage PyTorch CUDA graphs to minimize the overhead associated with launching kernels during speculative decoding. To perform sampling without replacement, which isn't efficiently supported in PyTorch 2.1, we employed the exponential sort algorithm in conjunction with PyTorch CUDA graphs. Our main results show that SEQUOIA consistently improves the speed of LLM decoding across a variety of settings, temperatures, model pairs, and hardware configurations. We achieved a speedup of up to 4.04 times in the on-chip setting and up to 10.33 times in the offloading setting. This significant improvement is largely due to the considerable difference between computational capacity and memory bandwidth. We have included additional on-chip results for the L40 GPU in the appendix. Our analysis led to several interesting observations. Firstly, SEQUOIA tends to select much larger trees for the offloading setting compared to the on-chip setting. Secondly, the average number of generated tokens closely matches the speedup in wall clock time, especially when using JF68M as the draft model. This is largely thanks to the hardware-aware tree optimizer. Thirdly, the optimal trees identified by SEQUOIA for slightly different configurations can vary significantly. Fourthly, SEQUOIA opts for deeper trees at lower temperatures due to higher acceptance rates. Lastly, the optimal tree size for larger models tends to be smaller than for smaller models because the time taken to verify increases more rapidly with the number of candidate tokens. We also conducted ablation experiments to validate the scalability of the SEQUOIA tree construction algorithm, the robustness of its tree sampling and verification algorithm, and the effectiveness of the hardware-aware tree optimizer. In these experiments, we altered one element at a time to isolate and understand the benefits of each component of SEQUOIA. Our findings demonstrate that the SEQUOIA tree can generate up to 33% more tokens per decoding step compared to independent sequences, showcasing the efficiency of SEQUOIA's tree construction algorithm. For these tests, we used JAC-FRAM, Llama 68M as the draft model, Llama 2-13B as the target model, set the temperature to 0.6, and used CNN Daily Mail as the dataset. Section Summary. In this section, we evaluate the scalability of the SEQUOIA tree construction method by comparing it to k-independent sequences, using SEQUOIA's sampling and verification algorithm for both tree structures. The SEQUOIA tree can generate up to 33% more tokens per decoding step, showcasing the effectiveness of SEQUOIA's tree construction algorithm. Section: Tree Sampling and Verification. In this section, we delve into the comparison between the SEQUOIA sampling and verification algorithm and other methods such as SpecInfer and Top-K sampling, focusing on how they perform under various inference hyperparameters like temperature and top-P, while keeping the tree structure constant. We showcase the outcomes of these comparisons as we adjust the temperature, with top-P set to 1, and as we modify the top-P parameter, with temperature set to 1. Our findings reveal that SEQUOIA consistently outperforms the other methods, achieving speedups of up to 1.65 times and 1.27 times compared to SpecInfer and Top-K sampling, respectively. It's noteworthy that SEQUOIA maintains its superior performance across different settings of temperature and top-P, unlike Top-K sampling and SpecInfer, which tend to excel in specific conditions. For these experiments, we employed JAC-FRAM, Llama 68M as the draft model and Llama 2-7B as the target model, with a temperature setting of 0.6, using the CNN Daily Mail dataset and the SEQUOIA tree structure outlined in a previous table. Moving on to the hardware-aware tree optimizer, we highlight its effectiveness in this part of our discussion. By comparing the speedups achieved by SEQUOIA trees of various sizes to those selected by the hardware-aware tree optimizer, we demonstrate the optimizer's capability. The key advantage of the tree optimizer lies in its ability to limit the tree depth, thereby accelerating the speculation process and achieving greater end-to-end speedups than any of the SEQUOIA trees whose structures were initially chosen to maximize token generation rather than speedup. Furthermore, the optimizer is adept at automatically identifying the tree size that yields the highest overall speedup, showcasing its efficiency in optimizing for performance.